This video lesson is to help do a quick review on balancing redox equations, and we're going to start by looking at how we balance those that are in an acidic solution. So you should have this list of steps already copied in your notes, but a quick reminder, we're going to identify the elements that are both oxidized and reduced, write our individual half reaction, and then start by balancing all the atoms that are not hydrogen or oxygen. Do the oxygen, the hydrogen, take care of the charge, and then we're going to balance the overall electron transfer and combine our half reactions. So make sure you have this list of steps here, and we're going to refer to this as we go through our example problem. So let's copy our first example here into your notes. And first step says we want to look for each atom that is both, one is being oxidized, one is being reduced. We know that oxygen and hydrogen will have the same charge from left to right, so we can eliminate those and save ourselves some work. And we're going to then focus on finding the oxidation numbers of manganese and sulfur. So as we go through that, we find that we will end up having a +7 for the manganese on the reactant side, +2 on the product, and the sulfur going from a 4 to a 6. So now that we've identified those, we're able to write our separate half reactions. So we're going to look at where manganese shows up on the reactant and product side and copy the entire species that the manganese shows in for our one half reaction, and then for the sulfur, the entire species that they show up in for the second half reaction. So that allows us to write two half reactions as shown. The permanganate ion and the manganese 2 ion, and on our second half reaction, recognizing that the manganese, as it goes from a 7 to a 2, that can only happen if it is gaining electrons. Therefore, the manganese is being reduced, and the sulfur going from a 4 to 6, that can only happen if it's losing electrons, so it was oxidized. Remembering our helpful mnemonic, Leo goes Ger. If I lose electrons, I am oxidized. If I gain electrons, I am reduced. So now that we have our two half reactions, we're going to go and balance each of them individually. And let's start with the permanganate half reaction first. So first we look to see atoms other than hydrogen and oxygen. That would be manganese. There is only one of those on each side, so we proceed. Now we see we're going to address, when we look at our list of rules, the next one is to take care of balancing oxygens. On our reactant side, we have 4 oxygens. There are none on the product side, so I need to add more, and because it's in an acid solution, there are water molecules available, so we're going to use water as a source of oxygens, and I need 4 oxygens, so I put 4 waters on my product side. Next, we take care of addressing the hydrogens. So by adding the waters, I now have 8 hydrogens on the product side, none appearing on the reactant side. Because we are in an acidic solution, there are plenty of hydrogen ions floating around. So we will add 8 hydrogen ions to the reactant side. Be sure that you are careful and continue to copy the charges as you go along. Important for our next step. So oxidation reduction involves electrons and their transfer. So besides balancing the atoms that we've taken care of here, we need to also balance the charge. So when we look at our reactant side, we can see that we have 8 times a plus 1, so that would give us a plus 8. 1 times a minus 1, so minus 1 on our reactant side for a total of plus 7. On our product side, plus 2. So our charges are not balanced. The only option we have are electrons in order to balance the charge. So I see that I need to add 5 electrons to the reactant side in order to have a plus 2 be the number on both sides. So let's go ahead and do that, and now our reaction will show that we have 5 electrons added. Okay, so now we want to check here and say, before I continue, does this all make sense? So we can do a little check here and see that if we remember when we first started, we said that the manganese had a plus 7 oxidation number here, a plus 2. We see that to go from a 7 to a 2, that could only occur if manganese gained 5 electrons. So the 5 electrons that we're putting on the reactant side indeed does make sense. Okay, now we're going to go through the same procedure for our oxidation half reduction, or our oxidation half reaction. So let's copy that. And again, we're going to go through the same process. I check my non-hydrogen and oxygen atoms. That's sulfur. There's 1 on both sides. We proceed. We look at our oxygens. 3 on the left, 4 on the right. I need an additional oxygen, so I'm going to add 1 water molecule to our reactant side. Next, we checked our hydrogens. I now have a grand total of 4 hydrogens on the reactant side and 1 on the product, so I need to add 3 additional hydrogen ions to the product side. Doing our charge check, our reactant side, there are no ions, so I have 0. On the product side, I have a negative 1 plus 3 times a plus 1, so that is a positive 2. Again, the only thing we can use to balance charge are electrons, so I'm going to need to add 2 electrons to my product side. So we go ahead and do that. And we stop and check that it makes sense. We had our sulfur going from a plus 4 to a plus 6. So that means that it has lost 2 electrons. So it makes sense when we look at our oxidation half reaction. Okay, now if we look back at your notes where you have your steps for balancing a redox reaction in acid solution, see, now we're at the point where we need to balance the total transfer of electrons. So we need to equalize our electron transfer, and that means we're going to need to look at the 2 half reactions together. So right now, our reduction reaction involves 5 electrons. The oxidation involves 2. So we start thinking of a common multiple. We quickly realize that that is 10. So in order to have 10 electrons gained and lost, I'm going to need to multiply my reduction reaction by 2 and my oxidation reaction by 5. So that means I have to look at each coefficient throughout the whole equation, and we go from 5 electrons to 10, 8 to 16 hydrogens, etc., all the way through. following through with our oxidation half reaction and multiplying everything by 5, we have the half reaction as shown here on this slide. So at this point, you know that you're correct if you have same number of electrons being transferred in both your reduction and oxidation reaction. So we're almost done. At this point, we're simply going to combine and simplify, and then we can do our final check. So we look at our two half reactions, and we're going to cancel everything that we can. So immediately we have 10 electrons on either side, and we're treating this much like we do in algebra class, where our arrows are representing an equal sign. So long as I have a common variable, in this case a species, on both sides, we can reduce it just as we would in math. So we look at our waters. I have 5 on my reactant side, and there are 8 showing up on the product side. So all 5 would be lost here in the reactant side, leaving a net of 3 waters on our product side. We see the only other component that we can reduce are our hydrogen ions. We have 15 on the product side, 16 on the reactant, so all would be gone from the product side, leaving a net of 1 on the reactant side. Now we just gather all the components that are on the reactant side in the 2 equations and add them together, and all those that are on the product side in the 2 equations. And that leaves us with our final reaction here. 2 permanganates plus H plus 5H2SO3 yields 2 manganese 2 ions plus 3H2O plus 5HSO4 minus. Now the nice thing about doing a redox reaction is that you know you're correct when you're finished. We can do a check. We're going to check that elements and charges balance. So for our elements, we have manganese, oxygen, hydrogen, and sulfur to check. Looking for manganese, we have 2 on both sides. Oxygen, we'd have 2 times 4 for 8, plus 5 times 3 is 15 for 23. And on the other side, 3 plus 20, we also have 23. Hydrogen, 1 here, plus 5 times 2 is 10. And on the other side, 3 times 2 is 6, plus 5 is 11. And I couldn't add there on the left, 5. 10 plus 1 is 11. So 11 both sides, it does check. Sulfurs, 5 both ways, we are good there as well. So we find that our atoms check. Now we want to check on the overall charge has to be balanced. So be careful, this is why it's important that you don't lose your ion charge signs as you're going through this detailed process. So on the reactant side, I'm going to say 2 times a minus 1 for the manganese, and 1 times a plus 1 for the hydrogen, 5 times 0 for our compound. On the product side, 2 times a plus 2 for the manganese, 3 times 0 for our compound, the water, and 5 times a minus 1 for our final ion. Do these 2 numbers add up to be the same on both sides? We find that we have a -1 equals a -1, and indeed it checks. So our final balanced reaction is shown here using what we call the half reaction method.